All right, let's take a break from all the abstract theory, talk about finite fields a little bit. These are very interesting, has lots of applications in coding theory, this and that. And they're also extremely important in number theory, and they're just very beautiful. Let's start with some examples. You know, field of order, prime order already, Z mod P. So where P is a prime. So these are easiest to describe. But then, now that we know this theory of extension fields, we can construct other things as well. So for example, take a polynomial, irreducible polynomial. Qx Px in Z mod P adjoint X of degree n. By the way, these are called FP when we are talking about them as fields. So take a polynomial in Fpx, so coefficients in Fp of degree n. And then we know this now is an extension field of Fp, and it is a field containing Fp and of degree equal to the degree of the polynomial. So K is an n-dimensional vector space over Fp. So this is a field of size p to the n. And in fact, all finite fields up to isomorphism can be constructed like this. So an example would be, so like if you take this one, let's say this is, consider this as a polynomial with coefficients in Z mod 2. Again, Z mod 2 and F2 are the same thing. When I write F2 when I want to think of this as a field. So verify this is irreducible, that you cannot factor. That's super easy to verify. If it did factor, it has to factor as a degree 1 times a degree 2, because Px has degree 3. And if it has a degree 1 factor, then it would have a root in F2. But this certainly does not have a root in F2. See, F0 is 1, but P0 is 1, but P1 is also 1 plus 1 plus 1, 1. So it doesn't have a root, so it's irreducible. So if you take this is a field of order 8. Okay. And in fact, if you can show that there is a irreducible polynomial of any degree over any Fp, then you would have one field for every prime power order. But we are sort of going to take a different path. At any rate, the big theorem is going to be that for every prime number p and every natural number n, there is a finite field f sub p to the n of order p to the power n. And so that we sort of see the indication of already, the existence part. But then there is this very strong uniqueness. Any finite field is isomorphic to one of these. So that tells you that there is only one field of size 81 up to isomorphism, etc. So for any given order, there is only one, and there is one if the order is a prime power. Okay? So proving this theorem would require a little bit of preparation. So I'm going to talk about a couple of things. One is characteristic of a field, which we haven't gotten into. Maybe I defined it at some point. Characteristic of a ring even means smallest n bigger than 0 such that 1 plus 1 plus 1 n times gives you 0. And here the 1 means 1 of the ring, and 0 means 0 of the ring. Yeah. So Z mod 6 has characteristic 6, whereas Z has characteristic, we should say infinity, but somehow one says characteristic 0. So when this doesn't happen, then we say characteristic 0. Okay. Rational numbers or real numbers, these are characteristic 0. Whereas Z mod n has characteristic n. So the first observation is that exercise, if f is a field of finite characteristic, P, then P is a prime. It's because you take the 1 in the field and take the first time that you get 0. If n times 1 is 0, and if n is a composite number, then it will have a proper factor. And then d times some other thing would be n, which will be 0. But then these are two non-zero things in the field that multiply to 0. That cannot happen because the field doesn't have any zero divisor. Okay, so that's essentially the reason that characteristic of a field has to be a prime number always. So in particular, if f is a finite field, then it cannot have characteristic 0, because if you keep on adding 1, you cannot keep on getting new things forever, so it has to repeat after a while, and as soon as it repeats, it implies that at some point it has to become 0. Because if 15 copies of 1 is 12 copies of 1, then 3 copies of 1 give you 0. Yeah, so any finite field has finite characteristics, so it has characteristic equal to some prime. Then characteristic of f is a prime number. And there is one extremely important function on finite characteristic field called the Frobenius that we need to define as soon as possible. Let f be a field of characteristic p bigger than 0, meaning finite characteristic. Define sigma, that's the standard name for this, by sigma of x is x to the p. It's just the pth power map. Takes an element, raises it to the pth power. Then you observe this is a silly observation, but it's extremely important, that this is actually a field homomorphism. That sigma is a field homomorphism. In fact, a non-zero field homomorphism, so it's injective, because 1 goes to 1, of course. Field homomorphism means what? Means it preserves both addition and multiplication. Well, multiplication is all right, of course. Sigma of xy is x to the p, y to the p, which is sigma x, sigma y. And sigma of 1 is 1, that's fine too. But sigma of x plus y is x to the p plus y, is x plus y to the p. But then you notice that's same as x to the p plus y to the p, because all the other terms in the binomial expansion of x plus y to the p have coefficients that are divisible by p. So if you are in characteristic p, then all those middle coefficients are 0. So this wonderful formula is true, that x plus y to the p is x to the p plus y to the p when you are in characteristic p. But that's same as sigma of x plus sigma of y. So this is called the Frobenius. Sigma is called the Frobenius homomorphism. And it's an extremely simple thing, but it plays a very, very, very important role. The fact that it's a field map, that it preserves addition and multiplication. Okay. And the other thing that I quickly, so that's a little bit about finite characteristic fields. And the other preparation that I need is to talk about repeated roots. So there's this lemma. At least I can state it, I think. Let take a polynomial. This is general, but we'll apply it in our finite characteristic case. So f is some field, any field. A polynomial. I mean, this you may be familiar with from calculus. Has repeated roots in some extension k of f if and only if the polynomial fx and its derivative polynomial f prime x are not relatively prime. In fx, so they have a common factor. What is a repeated root? I mean, x minus 1 squared times x plus 2 has a repeated root. 1 is a root that repeats twice. Yeah. So when a power of a linear factor shows up, then we say that that root is repeated that many times. Whereas x minus 1 times x minus 2 times x minus 3, this has all distinct roots. There is no repeated root. Yeah, so 2, we say that 2 is the multiplicity of the root 1. If you call this polynomial fx, then 1 is a repeated root. And you know this actually, that if at least if it has a repeated root, that means that the square divides, so the derivative would still be divisible by x minus 1. So x minus 1 will be a common factor of fx and f prime x. And that's essentially the proof. Maybe I can write down a little bit, at least one way. And then I'll let you look at the rest. Let's do this implication. So suppose f GCD of f and f prime is 1. So they have no common factor. Then there exists g and h such that gf plus h f prime equal to 1 for some g and h in fx. Yeah. So if a is a repeated root of fx, then fx is divisible by x minus a square at least. So f prime x is, so x minus a divides both f and f prime. But that tells you from here that x minus a divides 1, which is a contradiction. Yeah, and I'll let you read the rest. So that's why this lemma is true. So now I think we have all the background to attack this theorem next time.